All right. Sorry for starting with a bit of delay. This morning, Sergei Dubovsky is gonna kick off our third day because he's not using slides. I have no idea what he's gonna talk about. So
We're on the same page. Let me thank the organizers and all the participants for this wonderful conference. And my title is Confining strings. This talk is based on discussions which we have with Gabriel Kuoma and Sasha Dedler. And I think it's fair to say that we're probably reaching the stage when this can be called work in progress. Well, meaning that we started with a large question, big question, and what we're mostly doing so far, we're educating ourselves and trying to reduce this question to maybe smaller ones, but concrete. And so let me update you on where we are. And I also, perhaps there are people in the audience who are better educated on the subject than we are. So I'm definitely will appreciate all possible feedback and suggestions for what can be done, or suggestions why we shouldn't be doing what we're doing. So, well, the big question is, and we formulated this basically in a very, as all big questions, and we formulated in a very ambitious way. What is the space of perturbative string series? And then I'm entirely say what I mean by this, but to explain what I mean, it's better to start with just, we had two classes of examples, so, and one critical strings of various kinds, and another class of examples confining strings in QCD-like series, basically, and CUM young males. And for me, the defining and interesting feature of both of these classes of examples is that series which support string-like objects. So there is a one-dimensional object there. And there is a decoupling limit, which in this case corresponds to limit G string going to 0, and in this case corresponds to limit n going to infinity, such that in this limit the worldsheet dynamics of this object decouples from the rest, and one gets the unique complete two-dimensional series living on the worldsheet. And well, that's roughly speaking what I mean here. Of course, I really want to be more ambitious and fun things that, well, in this case, there is in both of these examples there is also genus expansion. So not only there is this isolated object, but also dynamics of the whole theory can be understood as a perturbation theory using genus expansion based on this one-dimensional object. So expectation I include that in that question, that expectation. But I think there is belief or expectation that really they are not two different examples, but they're that is a way to embed second example in the first. But we're not that yet, far from being there yet. So for the purpose of the talk, I will focus on the second class of theories. And basically, the question I'm trying to ask is kind of what are there other different confining strings which are not like these ones. And well, the first thing which might come to mind to consider different Lie groups, but of course, in the end, the infinity limit, known since early 80s, all the series up to some, basically up to some global projections, but they enter infinity limit, they all reduce to the same theory. The most pedestrian way to understand it is that if you think of, they're all described by double line top diagrams. And so the difference is SUN and SON, that in one case there's orientation, in another case there is no orientation, so you make some projection, but otherwise one gets the same theory. So we don't get anything new. Well, and moreover, it's clear just from thinking about this example for D young meals, it's clear that this theory is quite rigid because there's no relevant or marginal deformations. So the theory on a flux tube it really looks like an isolated theory, and that also makes it useful to apply bootstrap methods to it. But still, it's kind of interesting to ask the question: are there any other options leading to something different? And what we're trying to explore, the possibility. Okay. Let's exhaust all the options with the Lie groups. So what about finite groups? And well, the nice thing that all simple finite groups are classified, so that there is a finite landscape here to study. And basically there are there are three families. So we're looking for some family of series labeled by some parameter n, such that when n goes to infinity, that there is Dopf-like limit. And if you look at the atlas of finite groups, and there are three families. So there are the simplest one, the n's, abelian groups. Then there are permutation groups. And finally, there are what's called finite groups of Lie type. Well, this is the whole zoo here, but roughly speaking, with something which can be called SU and Q, S L and Q, where Q the power of the prime number. I won't try to define all of them, but just to give you an idea, the simplest case would be, for instance, consider SL and P. So SL and P would be the group with entries being so. SL and P is the matrices where matrix elements are residues, so the element of the ZP, and one imposes condition that the determinant is equal to 1 mod P. And there is kind of generalization of this construction where instead of just residues mod P, one uses the finite fields, finite fields. Yes.
What about the hidden? I mean, they have an arbitrary rank. Or are they simple?
They're not simple, right?
Oh, you don't want to talk about them?
Yeah, monster group, no, because in this family, there are just like for Lie groups, there are regular series, but then there are exceptional groups. And for finite groups, there are more exceptional groups than for Lie groups, and more monster group, it appears there, but I don't care about them because there is no n like parameter for them, right? So Yeah, I think the answer would be that those are not simple, but, right. Okay, so. Well, then. Yeah, so there is a generalization of kind of this for not based on just residues mod P, but on finite fields and on unitary groups. There is kind of one can construct analog with unitary groups right, as a SLNQ. And so what I mean by finite group gauge theory is that we're defining them, well, usually on a lattice, and we're thinking about action, which is product over links, over so there is a group element, just in the usual way. There is a group element living on every link, where then there is that's product over links, sum over group elements instead of integral as for the groups, and then there is an action where in the simplest form of the action to be would be that it's given analog of the Wilson action here. Comes to the sum over the plaquettes, where plaquette action is just something like the character of the plaquette, which is the product of group elements of those plaquette, in some representation of the group. So we're thinking about this kind of theories, and right away it's clear that there are two separate questions. One question is existence of continuum limit, and second question, existence of soft-like limit. And of course, a priori, in principle, we want to find an example where there is a positive, non-trivial answer to both of these questions. Yes.
Now, usually there's a third very important thing, which is whether there are actually confining districts. Because I would guess, for example, with the NH theory, in a continuum limit, it was the one percentage of things is lower.
Well, first of all, well, it's kind of, in some sense, it's related to this because I think that's this the starting point. If one doesn't care about continuum limit, starting from strong coupling expansion, then there are confining strings. Now, and there are definitely examples of confining series of this kind. So, for instance, probably the most familiar one, probably counterexample to what you just said, namely in 3D, one can see the Z2 gauge theory. In 3D, that's the same as 3D Ising model. Well, it's projection of parity even sector of 3D Ising model. So there are definitely examples.
Continuum limit of Z2 as gauge theory, a continuum.
Yeah, that's
BF theory,
huh?
which is a continuum limit of Z2 as gauge theory is BF theory.
No. I'm not talking about topological theory. The Z2 lattice gauge theory has a fixed point, which is Ising model, and there are two phases. So there is the
Talking about the transition point between the last confining phase and the BF phase.
yeah, right. And
Okay.
right. So that's kind of one example, which is one of the examples which triggers, but it looks like there is, and to my knowledge, it wasn't. That's already interesting example. So one may wonder, are there more interesting theories here? And to my knowledge, it wasn't studied systematically. Right?
I know it's a counterexample to what I said. It's the CFP. It's not going to be confined either.
No, but you can deform it, and when you're in the massive phase, you get the main walls between ice and vacuum. That's confining strength. Yeah. So, no, it is example, but it's not Lagen example. So now, well, I'm not sure I will do on time. So let me tell you right away, kind of our expectation. So there's this three family of series. So our expectation what we think and how they do in terms of realizing the initial goal, namely realizing examples of weakly coupled strings, confining strings. So, well, the first one, I think it's pretty clear. One doesn't expect that to be a successful story. So here at n to infinity limit, one expects to recover the U1 theory. And that's the case. In the second case, that's actually what we're mostly focused at the moment. And I'm not sure Gabriel would agree with me, but it's okay. I tell you my okay. My expectation here is that the answer will be negative. So that's there may be a Lagian limit, but it's not that limit. We can kind of oscillating between different answers, but so far it looks to, I think the latest it looks like it will be not a weakly coupled string theory. And well, here I have the least to say, but hopefully yes. Hopefully the answer will be yes, but it's not based. It's just based on my optimism. So, well, and kind of this example looks more similar. At least superficially, this family of series looks more similar to SUN gauge series. And well, I think what the dream is that what's interesting here is that there is an additional parameter, right? So kind of the great contribution of Holt was to identify expansion parameter in QCD, which is n, but here we have another parameter, which is well, this Q or P. And so one may dream of now looking at this two-dimensional plane, and we know that for Lie groups, just for SUN series, that for instance, that's like understanding confining things is hard, that the theory on the bullshit say is not integrable. So one may hope that maybe somewhere here, like the most optimistic scenario would be that maybe somewhere here in this plane there are some solvable big models. And at the same time, maybe, and again, it's just based on nothing what I'm just saying, but some kind of optimism, maybe there is some kind of scaling limit when one does something like this, n to infinity and p to infinity, which would allow to restore SUN series also. But yeah.
Why? So normally for the hook limit, I would take the gauge count scaling. So that would be one of the beta parameters. Why not that? Yeah, to define the hook limit, normally we scale a squared along the right. Now what would be squared in this context is basically beta.
No, but there's no such a parameter in QCD as gauge count. Right? We take an n to infinity. That's the only parameter which here. Keep an under QCD fixed.
Keeping the QCD fixed.
Right.
The analog of down the lattice is nothing but the lattice beta parameter.
Yeah, that's what I have in mind. But what I mean by top like limit is that I have in mind taking such a limit, but I want asking the question whether in that limit, so in the strong coupled expansion we have confining strings. So whether those confining strings, whether they survive and continuing limit, and whether they become weakly coupled in this. That's what I mean by top like. One gets a really genius expansion, one gets a weakly coupled string theory. So that's so I have how much time I have?
7 minutes.
7 minutes, okay. So yeah, let me then, because I meant to say a few words about the end, because that for me was the entry to the subject that I did some work with someone called Mike Decker and Andreas on the lattice study, studying the example. But let me skip that because it's really. Let me tell you a few words why, how we think about how we're trying to approach these two cases, which are more interesting definitely. And so first of all, because we want to disentangle these two questions, existence of continuum limit and existence of top-like limit, what we started with, we were looking at the 2D case. We're looking at the 2D finite group Yang-Mills theory. And the reason is that in 2D, there is a way to formulate the theory such that it's, if one kind of sticks to this formulation with which I presented here, then it's still not clear that there is a continuum limit, because there is no naive continuum limits. Well, essentially because no Lie group. So, but it was known since 70s. So there is another way to write the action, which, well, a different name. Actually, it was Migdal Kadar form or something like that. But basically, one more. So here, the action is product of P minus SP, where SP is a plaquette action, and Topolman does one writes the action, writes plaquette action as a sum of our characters. So these are R's are representations. The R's are parameters of series, are constant parameters, which you think about them Kaplan constants. And so any class function, this action should be class function of the plaquette for Gaussian values. Any class function that is the sum of characters, and this dr is a dimensionality of corresponding representation. And the nice thing about writing action in this form, which was noted by Migdal, is that it allows to do the following. So if you have the two plaquettes, then if you sum over group integrate or sum, that's both works in the same way for continuum group and for finite groups, for finite groups, then what one gets, so the, one gets now action of the same form on the double plaquette, where this factor gets squared, and that just immediately follows from orthogonality formulas for group characters, and so that so basically that tells that something was also mentioned yesterday, right? So the 2D Yang-Mills is essentially one plaquette model, so one can reduce all the series to just calculation of a single plaquette, and one gets here the power of this plaquette, and that immediately leads to Wilson to area law for Wilson loops, and also it tells essentially it tells us how we want to define the parameter of the series so that we have a continuum limit. Namely, one takes these ZRs as sigma r a squared, where sigma r is a tension of a string in the corresponding representation of the gauge group. So if one takes action of this form and calculates different Wilson loops, then one gets area law with finite tension. And for Lie groups, if I start with Yang-Mills theory, then this sigma r, if I start with the standard action takes a Fourier squared and takes naive continuum limit, then this would this sigma r would correspond to Kazi loops. But in principle, one can play this game for arbitrary finite groups also, and this theory has a continuum limit in the sense that there are finite tensions. And in particular, one can, like one exercise which we're meaning to do is one can repeat for instance what Ross and Taylor did, but for instead of for this kind of characters based on finite groups, and to see what of Gross and Taylor, what they observe for young Mills works, what doesn't work. But that's kind of the first stage, the first step, and what we want to have a weakly coupled string theory. We want to find factorization of Lagian factorization of Wilson loops. All right, so one wants to find the property that when n goes to infinity, that the expectation values of Wilson loops factorizes. For this kind of series, which sometimes called quasi-topological series, because they reduce to this series, this property which I described here, it's related to volume area preserving differential symmetry of Urian-Mills theory. Okay, so I'm almost I'm out of my time. So let me just tell you, even one more minute, what I'll tell why you think that for a SN group, we think the answer is no, that there is no top-type limit, there is no weakly coupled string theory. So naively, it looks like one. So the question about Wilson loop factorization is this language reduces about assigning tensions to different representations. And naively, it looked to us that we can assign these tensions, which will be more or less the same way, because the structure of many representations of SN is the same as structure of ON. And so it looked like we could assign these tensions. But then we started thinking about strong coupling expansion of this theory. And in strong coupling expansion, one needs to deal with integrals, say, for SUN group, and one has a bunch of integrals of this kind, I1, I2, I1, J2, etc. And one can show that there is a genus expansion in the strong coupling limit, which is basically follows from the fact that the only invariance, if you have not too many of these U's, that all invariants, this kind of integrals, they will have the form of some delta ij, not ij, with different index assignments. So that's the only invariance which one can build up until one reaches take n of these, when there is also epsilon delta. And based on this one, kind of has usual double line. Now the observation is that for SN groups, starting from tensors of rank 3, there are additional invariants. So Eijk for 3 indices, it's 1 when I equals j equal to k and 0 otherwise. So at each starting with 3 legs, one gets this invariance, and there will be infinite set of these invariants which appear in these terms in the strong coupling expansion, which kind of spoil at least the standard argument why there will be genus expansion, but also on more physical terms, that's the statement. So kind of for SUN, this epsilon tensor, which I told you about, that's what's also called baryonic vortex, right? That's the fact that you can take n fundamental strings. That's we expect to have it inside the proton. If you take n fundamental strings, there's a junction combining these n fundamental strings. But because it's n, at large n limit, that this vertex is heavy, so it's kind of, it doesn't spoil perturbativity of one-of-n expansion. But here in the SN-like series, the presence of this invariance tells that these kind of junctions appear at order 1. And this in holographic constructions, for instance, these junctions are associated with d-branes, so they're non-perturbative effects. But here in SN series, this kind of non-perturbative effects appear without any suppression by n calculus. So that's actually the moral reason why we think that there will be no, this series will not look just like weakly coupled strings. But I think I should stop now.
More questions for Sergei?
Isn't there a different approach to this question of what is the space in perturbative string theories? Just assume the existence of a genus expansion and put in, and then look for consistent, hence, string junctions, and then ask that then test unitarity and. In other words, instead of. Guessing a class, lattice models.
But
And then just trying to construct the string motivation. System.
well, for instance, does it sound feasible to say recognize SUN confining strings in this way? It seems hard, but
Maybe part of
no, definitely that sounds like a priori that sounds like an approach. But here, well, we're trying to find something where we can start to do some calculations and kind of our approach is basically trying to do a strong coupling expansion of this series, which sounds and gross type Taylor type exercises with this series, which sounds like a set of concrete calculations which I can do that. It will be, of course, very interesting. Yes.
There is an interesting H theory that you can argue is it's the same direct product of the permutation group Sn if you want to do n minus one.
Okay.
So it's interesting because the center of this Cn, but the non-invertible symmetry, the straight spectrum is much richer. Where does it fit into your paradigm?
Well, it's not.
Very comfortable theory, by the way.
No, it's just for here for maybe arbitrary reason, we just started looking at simple groups, but definitely one can consider the series. Well, yeah. But I would expect, at least my expectation would be that if Sn, large n limit of Sn theory doesn't give just weakly coupled strings, I don't expect that multiplying by some UN factors would help. But
Also, one more question. You didn't talk about the symmetries of some of the theories, and sometimes they have very, unexpected symmetry. For example, to the idea of symmetry and then again, non-invertible symmetry. Which you classify the string tension, where it can be explained representation of numbers. Do you know the symmetry of all of these phases? Is there a non-invertible one-form symmetry in all of these?
no, I don't know. I'm not sure. I don't think it was studied. Right, but that's just because the series is topological.
The universe is not stable, so it's a non-inverted symmetry because the Jewish part of the world.
Last question.
Just a suggestion that if you want to look for strings that are gonna resemble what you're getting at those. The thing to do is to check the symmetry, look for something that is EN multiple string. In binary dimension.
Well, I'm not sure because, for instance, ON theory doesn't have the
But at large n, it doesn't matter. There are.
yeah, but it's yeah.
So, but as a start, I mean, the list of examples you gave, certainly the CN example will not,
Yeah, but also this,
possibly some of the other ones.
yeah, because this all these groups they have a center. Right? So,
SN is gonna be.
no, center. Yeah, that was also initially that was also one of the intuition why this SN doesn't look with certain point why this series has the n form symmetry. That's right. But I'm not. But I sympathize with what you're saying, but I'm not sure.
Oh, I have one more remark about SUSOSP. There's a network from early 80s by Lovelace.
Yes, that's what I refer to. Yeah, the loop equations.
Non-perturbative in this.
Right, because loop equations look the same in all these series. Actually, interesting related question, which also kind of motivated what we are doing, because Martin kind of was doing recently very interesting bootstrap for loop equations. So the question is whether that can be generalized for this finite group gauge series. For instance, the two gauge theory insert D is Ising. So that would be alternative way to bootstrap Ising. But right away, it's not obvious how to write, but it should be possible to do something like that. But it's something like interesting related question about this series. Are there version of loop equations for this finite group gauge series?
All right. Well, thanks again.